Hello everyone, welcome back. In this video, I want to start talking about and introduce ourselves to the complex number system. So we were just talking about simplifying radical expressions. Sometimes when we're working with these radicals and these square root formulas in particular, we end up trying to take the square root of a negative number, and a lot of times we'll stop right there and just be like, hey, we can't do this, or there must be no solutions. But that is not the full story. So it is true that there is no real number that corresponds to the square root of a negative number, but there are these other numbers that we call the complex numbers that allow us to work with square roots of negative numbers. And so here we're introducing this complex number system. The complex number system is denoted by this capital Blackboard C, and it's an extension of the real number system, which is denoted by this capital Blackboard R. And the real kind of initial objective of this complex number system is it allows us to work with these quantities that we run into pretty often, in particular, the square roots or even roots of negative numbers. And so oftentimes when we're working with the real number system, especially initially, we try to visualize it using the real number line. And that's what I have drawn on the board right here, the real number line. Here we can see a lot of nice integers labeled like -2, -1, 0, 1, 2, 3, and 4. And on this number line, we have a special spot for every single real number that exists. Like even the non-integer numbers like pi is like 3.14. That'd be really close to 3, like right about there or so. Or the square root of 2 is like 1.4 something, I think. That'd be some number somewhere between 1 and 2 on our real number line. But is there a spot for something like the square root of -4 or the square root of -1 on our real number line? And it turns out there is not. There's not a good spot where we could put like the square root of -1 or the square root of 4 here in any way that makes sense. So that's one of the many reasons why we need this complex number system. And this is just an introduction to the complex number system. But what's really interesting, if you want to take a deeper look at it, is essentially there's no spot on this axis for these square roots of negative numbers. They don't fit on the real number line. So kind of the solution to that is we introduce a second axis perpendicular to this that we call the imaginary axis and put those numbers on that axis instead. That actually makes everything work out very, very nicely, but unfortunately it's outside of the scope of what we're going to be doing with complex numbers in this class. So there are infinitely many negative numbers out there that we could take the square root of to start stumbling onto these complex numbers. But to make everything a little bit easier to work with, we usually kind of break things down using the square root of -1. That's what we refer to as the imaginary unit, or it's denoted with a special symbol, which is just the letter I. So if you see that letter I in your mathematical notation, it's most likely that that is denoting the imaginary unit, which is the square root of -1. And it has this property that it is this special number that when we square it, so I squared, it gives us back a negative number, in this case, -1. So oftentimes we're going to be combining quantities that we can take the square root of with quantities that we cannot take the square root of. And so when we put those pieces together, that's how we create these complex numbers. These complex numbers in general can be written in the following form of A plus B times I, where A and B are both real numbers, the numbers on the real number line that we are very comfortable with, and I is our imaginary unit representing the square root of -1. A is referred to as the real part of our complex number. And just that number B, that part that is multiplied by I or the square root of -1, that number B is referred to as the imaginary part. And so this is all really just notation so far. When we're actually working and doing arithmetic with our complex numbers like A plus BI, we really just follow the same set of rules we use when we're doing arithmetic with radical numbers or radical expressions, because after all, I really is just the square root of -1. So let's go ahead and check some of that arithmetic out, get a little bit more comfortable working with this new number system, the complex numbers. All right, so let's go ahead and look at some examples of doing some basic arithmetic with these complex numbers. And keep in mind, we're really just following the same set of rules for arithmetic that we use when we're working with radical expressions. And really, a lot of these quantities that we're going to be combining together and simplifying are going to work in the ways we intuitively expect them to. We just have to keep in mind that if we have something like I raised to the power of 2 or I squared, that we can turn into a factor of -1. So let's go ahead and look at this first expression. We have our first complex number, 5 minus 3i. Its real part is 5. Its imaginary part is -3. And we're adding that to another complex number, 6 plus 5i. The second complex number has a real part of 6 and an imaginary part of 5. So if we want to combine these two complex numbers together, we really just combine like terms together. So we can add the real parts together. 5 and 6 will combine together to give us 11. And then we can add together the imaginary parts, or the parts with a factor of I combined. Just like if we had like 5 minus 3x plus 6 plus 5x, we're combining this in the exact same way, just by combining terms that are alike. So again, the like terms here are 5 and 6. The real parts add together. We also combine the imaginary parts. They are also like terms. And -3 plus 5 gives us +2. And so that's our answer. 5 minus 3i plus 6 plus 5i is just 11 plus 2i when simplified. So now if we look at our next expression, we want to combine and simplify. Here we have a product of two complex numbers that are multiplied together. First we have 3 plus 2i, and that's getting multiplied with 1 minus I. And so when we're multiplying these together, just like when we multiply any binomials together, we have to use the distributive property and FOIL things out and expand. So when we're distributing, we have to distribute that first term of 3 to both terms in our second set of parentheses. So that'll give us 3 times 1, which is 3. Then we have to distribute it to 3 times -I, which will give us -3i. We have finished distributing that first term of 3 throughout our second quantity in parentheses. Now we have to distribute the second term of 2i throughout that second quantity in parentheses. So 2i will get distributed and multiplied with that first term of 1, but 1 times 2i is just 2i. And then 2i will get distributed and multiplied with -i as well. So 2i multiplied by -i is going to give us -2 times I squared. So we use the distributive property to expand this, or that special shortcut for the product of two binomials called foiling can also be used here. Remember, foiling, F-O-I-L, stands for adding together the product of the first terms. That's where our 3 came from. The outer terms, that's where our -3i came from. The I in FOIL is for the inner terms, 2i and 1, gave us that 2i. And then the L in FOIL is standing for the product of the last terms. That's 2i and -I. That's how we created that -2i squared. So we have expanded everything here in this product by using the distributive property or foiling, but we're not quite done yet because we can combine some like terms to finish this off. So we have this real number 3. We have these two imaginary numbers, -3i and 2i. We can combine those together because they are like terms, and -3 plus 2 is -1, so that's -1i. And then our last piece here, or this last term, is -2 times I squared. We have to remember, I, the imaginary unit, has that special property that when we square it, it turns into -1. So this -2 multiplied by I squared is really like -2 multiplied by -1. And well, the product of two negatives is a positive, so that turns into 3 minus I, but plus 2. And we can now simplify just one more piece a little bit further by combining those now obviously like real parts together. 3 plus 2 is 5. And so our final answer is 5 minus I. So the product of 3 plus 2i with 1 minus I gives us another complex number, 5 minus I. All right, so this last example is one that I just really want to do for fun. It's not something we encounter all the time, but it's still neat and kind of keeps us mindful of how these powers of I kind of interact. And so we have I to the power of 6, and we want to simplify this as much as possible. And the only thing we really maybe remember about I is that I squared is equal to -1. So what we can do is think about factoring I to the power of 6. It's really like I times I times I times I times I times I, right? We have 6 factors of I multiplied together. That's what that exponent notation means. but we can group these two factors of I together at a time. Or that's kind of a long way of saying, hey, we can use exponent rules to rewrite I to the sixth as I squared times I squared times I squared. But now every factor of I squared is equivalent to or can be swapped out and replaced with a factor of -1. So I squared times I squared times I squared is just -1 times -1 times -1, which is -1. So I to the sixth looks pretty complicated, at least initially, but when we simplify it, I to the sixth is really just a way to write -1 in a fancy, complex way.